I want to talk about points of inflection today and what is a point of inflection. This has come about because a friend of the channel, Jay Winfield, went on a teaching course for GCSE Further Maths this year. And while a conference with these other people who were on that course, the table got discussing what inflection points were, and everyone on his table was trying to tell him that inflection points are just this, right? They just go up flat and then go up again, or they come down flat, come down again, either one. And Jay Winfield, being a much better mathematician than any of them, sort of knew that they were wrong about that. He sort of knew this wasn't an inflection point, or that it is, but it's just not the whole story. Um, but wasn't quite sure how to, and couldn't convince them, right? He couldn't convince them that they were wrong, probably because he wasn't quite sure enough about all the fine details to be convincing about it. And it occurs to me that if a group of teachers who are on a CPD course to teach maths better, if a group of them don't even know what an inflection point is, and basically no teachers that I've ever talked to know what an inflection point is, then it occurs to me that basically no students will know what an inflection point is, because if the teachers don't, how on earth are the students going to know? This video probably won't do the whole thing, but I'm going to talk about a fair few things. The problem with this picture here, to get us started, is that this is a bit like saying, what is a mammal, and then providing this picture. Most of us are aware that this is a technically correct answer, because this is a giraffe, and giraffes are a mammal. And being vaguely intelligent people, we can infer that, okay, so it's a giraffe, it means mammal, yeah, cool, this is correct. But it's not really correct, though, because if someone has no idea what a mammal is, think of all the incorrect things they're going to infer from this picture, right? They could infer that giraffes are just the only, like, giraffes are mammals. The only thing that's a mammal is a giraffe. They could infer, of course, that a mammal is a soft, cuddly toy, right? You can infer a lot of incredibly wrong things by just giving this thing out here, even though it's technically correct. And exactly the same thing is happening here, right? This is technically correct. This is an example, a very niche example of an inflection point, but it's not representing every inflection point. There are lots of things that look rather different that are also inflection points. And I think that's what we need to get through. There's the textbook doesn't do a good job helping out here. Because this is what it has in its differentiation chapter. It says maximum if the derivative goes positive, 0, negative, minimum if it goes negative, 0, positive, and then point of inflection if it goes negative, 0, negative, or positive, 0, positive. So it's just saying the gradient goes positive, 0, positive, or negative, 0, negative. Well, this one here goes positive, 0, positive, right? And then the negative, 0, negative is that. So this is just saying what I've just said on the previous slide, but in table form, and it's wrong, right? Except it's not wrong, it's right. This is an example of a point of inflection of both of these things. Examples of point inflections, but they're not what it is, right? This is just more of this stuff. And we can prove it, right? If we go to Wolfram Alpha, which we of course know is always correct, no matter what anyone tells you ever, and you say, what's the point inflection of this cubic? It randomly gives you a point here, which looks remarkably different to this one here, right? It's not flat, for a start. It's not flat. So there must be something more important going on here if Wolfram Alpha thinks this is an inflection point. Likewise, if you ask it what the inflection points of sine are, it suddenly highlights all of the roots of sine. So there's actually an infinite number of inflection points in sine, and it's just all of the roots. So what's Wolfram doing here? Like, why does it think these are inflections? So, okay, what we need to talk about is what this table is really saying. If your gradient is going from positive to 0 to negative, that means the gradient of the gradient is negative, right? Because you're getting smaller. Imagine this is a number line. You're going from the positive to 0 to negative. You're getting smaller. So the gradient of the gradient, the second derivative, is negative. Likewise, this one's positive, right? Because you're going negative to 0 to positive. You're getting bigger, literally. Here, neither of those things are happening, right? You must be getting bigger to go from negative numbers to 0, but then you're getting smaller again to go back into the negatives. So you're just kind of, if you think of it on a number line, you're coming to 0, and then you're just going back through the negatives again. Likewise here, you start positive, you go to 0, but then you come positive again. The second derivative isn't doing anything consistent there. It's changing halfway through. But one thing you might want to say is exactly that. There's a change in sign of f dash dashed, right? In the sense that, again, if we think of this one here, we're starting the positives, going to 0, going to positive, the gradient of the gradient was negative because it was getting smaller, but then it became positive because we start getting bigger again. So there's a change in sign of that. And maybe that implies that means that somewhere f dash dashed is 0, which is what the textbook says. F dash dash of 0 says it could be an inflection point. Because if f dash dash was 0, that means, to go from negative, thinking about this change in sign, to go from negative to positive, you've got to go through 0, right? Or to go from positive to negative, you've got to go through 0. So maybe we can come up with this idea that points of inflection don't care about the gradient itself. They care about the derivative of the gradient, so the second derivative. And it happens when you go negative 0 positive or positive 0 negative. Right? Maybe we can make a table that looks a bit like this, and this will be much more clear for us. Um, Now, the reason that it's only sometimes is because, of course, the case that we were discussing before, what if it's negative 0 negative? Well, that doesn't work. That's not a point of inflection, right? Because there hasn't been a change in sign. You've just been positive to 0, which doesn't really have a sign, back to positive again. There's no change in sign of f dash dash there. So that's why the book says it could be one of these things, but it also might not be. So yeah, maybe though, maybe a necessary condition to get from negative to positive, to get a change in sign, maybe a necessary condition is that f dash dash needs to be 0 somewhere. Maybe that's necessary. Okay, it's not sufficient because, of course, negative 0 negative, as I've said. So let's think about this function here. This is a cubic. Let's derive it and let's derive it again. And of course, we were just talking about f dash dash being 0. So let's set this to 0. Well, that's clearly when x is 0. Which of course you can sub in and get y as 5. Then if you graph it, you end up with this graph here. So this has an inflection point here. I'm sorry, just here. I thought I'd highlighted it, but just here. Which is cool. It has an inflection point. It doesn't go flat anywhere because the first derivative doesn't matter. Hopefully we've got through that. But it has an inflection point here. That's kind of interesting. So this is a well-behaved function that just has a well-behaved inflection point, and we're good to go. Cool. Now, what about another one then? I should probably have checked that dy by dx is positive and negative either side, which I didn't do because I couldn't be bothered. Is it though? So sorry, that d2y is positively negative. Sorry, going back to this table. Just check that if f dash dash is 0, it goes negative positive or positive negative either side. Of course, here if you put in a number slightly less than 0 either side of this, or slightly bigger than 0, it's going to, of course, be negative, then 0, then positive, because this is just a linear function. So yeah, this is an inflection point. Good. I didn't get that wrong. Y equals sine of x, if we derive and derive again, and then set to 0, well, minus sine of x is equal to 0, and all the time sine of x is equal to 0. So suddenly the Wolfram alpha thing makes sense, because, of course, all the roots, when sine of x equals 0, are going to lead to the inflection points when minus sine of x equals 0. So that's pretty cool. And again, check what happens if you're just either side of 0. But of course, because sine looks like this, one side of 0 you're negative, one side you're positive. So yeah, these are all inflection points. I mean, we might need some more work to definitely show that. But yeah, these two functions here, the ones that I just shown, the sine graph and the cubic, well-behaved functions, have nice inflection points based on c2y by dx squared being equal to 0. Unfortunately, it doesn't end up being that nice all the time. For example, this function here, if we derive again and set to 0, we get x is 0, of course. Now, that's not an inflection point at all. And the reason it's not is because, again, it hasn't followed this table. When you put in a slightly negative number, you get a positive here. And when you put in a slightly positive number, you get a positive here. So it goes positive, 0, positive. So as I've been trying to say maybe this whole time, it's not enough to check that f dash dash is just 0. You can't just do that. You have to check either side. So this is not an inflection point. You can't just double derive and set to 0. You'd have to check either side for cases like this. Then you have cases that look like this, and this one is not nice either. We derive again. I'm going to skip through that mostly. We set to 0. Now the problem with this is that doesn't have an answer here. This doesn't have an answer because it's minus 2 over 9x to the power 5 thirds, and then you times both sides by 9x to the power 5 thirds, and you get 2 equals 0. There's no solution to x here. So the double derivative of this function is never 0. However, this does have an inflection point. It has an inflection point at 0, even though the second derivative doesn't actually ever equal 0. And the reason that we're allowed to do that is because it's still the double derivative. If you put in a slightly negative number, this is negative. But if you put in a slightly positive number, in fact, or is that positive because of the two negatives? It doesn't really matter. It goes negative 0. Sorry, it goes negative doesn't exist positive, or positive doesn't exist negative. You don't actually have to go through 0, which is kind of interesting. So that initial thing that we said about functions having to glide through from negative to positive doesn't actually have to happen. You can have no second derivative not kind of existing. It's almost like you've gone so far back through the negatives you've arrived at the positives magically, kind of thing. But anyway, this has an inflection point. The other definition you see of inflection points is something that goes from concave to convex, which you can see that this graph does. I mean, mostly if you just turn your head to the side, this just looks like the classic inflection point you all had in your heads 10 minutes ago. So yeah, that's kind of cool. Anyway, you don't have to have f double dashed equals 0. It's not actually necessary. Um, cool. This function here is just the last one I wanted to talk about, I think. So we derive again. This clearly never equals 0 because it's 2 over x cubed equals 0. If you did again end up with this 2 equals 0 idea. Um, however, I'm only kind of bringing this function up because it's worth being careful. If you say, okay, well, this function doesn't equal 0, but actually, if you evaluate slightly less than 0, you get a negative here. If you evaluate slightly bigger than 0, you get a positive, but it doesn't exist in the middle, but that's fine. We just saw an example where it doesn't matter if it doesn't exist in the middle. This one does matter because the function itself doesn't exist at x equals 0. You can't have an inflection point where the function itself doesn't exist. Here, the function did exist at 0, right? You can just put in x equals 0, you get y is 0. But here, the function doesn't exist. So you do have to check that the function, if you're going to go down this route, you do have to check that the function does indeed exist. Otherwise, you're going to be not correct about it. You can use an Euler diagram for this. So it has a point inflection, d2y by dx equals 0. We've got the well-behaved functions in the middle, like sine x and this one here, the cubics. Then you have the ones that have a point of inflection but never do this, like this one. And then you have the ones that do this but don't have a point inflection because when you do y double dashed, you don't get negative 0 positive, you get positive 0 positive. So yeah, this is kind of the diagram that sort of tells you that kind of thing. Okay, so I want to talk about something slightly different now, which I think is actually, maybe I shouldn't have left it to last because I think it's the most interesting thing about all of this. Um, there's a theorem here that says all cubics have rotational symmetry around some point. So I'm sort of talking about something completely different now. I'm suggesting that if you take a cubic, picture a cubic in your mind, there's some point on that cubic by which you can turn the cubic, rotate it all the way around, and it will have rotational symmetry order 2. Let's just prove that really quickly. And to prove it, so yeah, there's the cubic. There's some point here where if you rotate this around, it will match itself before having to rotate it all the way down 360. After rotating 180, it will match, and then another 180, and it will come back to where it was. Okay, so if we just move it this far to the right, of course, that's the function x minus b over a. Let's just work this out. It ends up looking gross, but the really good news is that this thing cancels with this thing over here, I think. Is it this thing and this thing? Some stuff cancels. This thing over there. I mean, I've typed it up, so I don't know why I'm guessing. This thing here and this thing here cancel, which is really nice. So you end up with this, and then what you can do is you can just replace this alpha, or I've just said alpha as this stuff here, just because I couldn't be bothered to write it, um, and beta, which is where I've written beta. I'm going to write it in a second. There we are. So yeah, I've replaced alpha here. Oh, sorry, that's still an A. Can't see my eyesight here. So yeah, we've grouped some stuff together. We've just made some substitutions, and we end up with a function that looks like this. And then of course you can just move the function b units up, or beta. Apparently, I wrote out fully. But if you do that, of course, when you move it up, this just goes away, and you end up with a really nice cubic function that just looks like this, and we'll just call it g of x. And yeah, by the way, maybe I could mention this is called a reduced cubic. If you ever learn anything about the history of maths, when people were learning cubics, actually it's called a depressed cubic, sorry, depressed cubic. When people were trying to learn how to solve cubics, it turns out that solving cubics like this is much easier than solving cubics that have an x squared term in the middle. So you'd always do this step first to get this, and then you could solve it using a formula. And then later they found a formula that did it for these. But for a time, it was really important to do that. Anyway, for now, we were focusing on moving it to the right and then moving it up b units. You end up with this function here. But this function here is kind of interesting because if you put in minus x, you end up just with the same function but negative. And that reminds me of I believe, an odd function, right? Because minus g of minus x is equal to g of x. So that's an odd function, which means that any value you put in on the negative x's is the same value. You get the same y value as you do if you put in positive x. It's just up here instead of down here, right? Like it's always reversed. But that's kind of what the definition of rotational symmetry is going to be, right? Like however far you are along here and upwards, you're the same along here and downwards, right? So this has definitely got rotational symmetry around the origin because of the symmetry by being an odd function. So what we've said here is if you take any old cubic and you just move it right and down, you end up with a cubic that has rotational symmetry for sure. Which means, of course, that the original function had rotational symmetry around the point that you sort of had the movement from. If you moved it back again, this point where 0, 0 would go to is the point with where the rotational symmetry is. And that's kind of interesting, but it's more interesting when you think about the inflection points of the same function. So if you derive and then derive again, and then set to 0, and then solve for x, you get this. And then if you put that into the function and get y out, you end up with this. And this is really interesting, and people who have been paying much closer attention than I have during this video will know exactly what I've done here, which is this function here, b over 3a. That was the exact amount. That's the x-coordinate of the inflection point, remember? It's the x-coordinate of the inflection point. That's the exact amount that I moved it to the right originally, right? And this function here, beta, the amount that I moved it down, is the y value of the function originally. So what I'm saying here is the inflection point of a cubic is a point of rotational symmetry. And I can sort of pseudo-prove that on GeoGebra. If you just take this one here, the inflection point is here, you can derive this a couple of times and show it if you want to. And if you take the rotation, after 180 degrees, it flips back to itself. And then after 180 degrees in the other direction, it also flips back to itself. And then, of course, after 360, it will become itself, of course, like everything does. But it's really cool that inflection points are actually points where the graph has rotational symmetry. Sort of. Again, there's so many sort ofs in here. This works for sine as well, by the way. So if you do sine, put an inflection point down, as we've seen, these are the roots, and then rotate it a little bit. I think it's this one this time. Sine rotates around its inflection points and has this symmetry as well. Now, this doesn't always work, except it sort of does, like I've said. Sometimes that rotational symmetry is global, and sometimes it's only local. So here's a quintic function, which has a point of inflection. I've done the maths to work out the point of inflection is here. And if you rotate that function around its point of inflection, using the other button apparently, you get a local rotational symmetry, but not a global one. And I'll zoom in maybe to prove this, or again, to pseudo-prove it. If I zoom in here and then rotate it around, there is going to be a local rotational symmetry in here. You can see this portion of the graph is matching itself perfectly. And if you zoom in, you can prove that even further. But it's not globally rotational symmetry. But inflection points, a really cool definition of them that you never see written down anywhere in school level maths is they're points of local rotational symmetry, which I just think is really interesting. Anyway, thank you for watching. I know that was quite a heavy video, but I think it is also quite interesting.